Okay, everyone, did you where's the sign up sheet?
Sign up sheet.
Sign up sheet.
Make sure you
Can I have it?
Okay. So before I go through, hi guys, excuse me. My name is Ariel. I'm teaching today's lab session. So before I start teaching, sign up. So before I start teaching, I have one question. What do you want to grab after today's session about separators?
How they work.
How it functions.
How they function. One point. What about the other one?
Any problems that we can see with them?
Design. Okay. Why do we need to know, okay, the functionality of the separator so we can design it properly? Okay. There are the two purposes of today's session. One is how it is operating. The second one is how to design it and why. So as you can see here, this is the separator. It does the three-phase separation. One, gas, and the other one is the separation between oil and liquids. What is the normal separation, three-phase separator type? Is it horizontal or vertical? It is horizontal. Why? And again, we're going to go through it thoroughly again. So let me just turn this on, okay, so you guys can see how it operates. Okay, so this is your production stream, let's say. It is gas, liquid, and water. It goes over here, it accumulates. So let's go. So you see it accumulates. So let me explain each part by part. So can someone tell what is this section called? Inlet diverter. So why is it, okay, that inlet diverter results in separation between phases? Can someone ask, let's say, Christian?
Which one?
Christian. Domin?
Yes, sir.
Yes, okay, so please you answer. Why do you think inlet inverter can actually help us separate?
Like you said yesterday in class, it redirects the direction.
Momentum, okay? What is momentum? M multiplied by V times V.
Right.
So the momentum of gas is usually less, is always actually less than liquid. So it can adjust the changes, while the liquid cannot. That makes separation from the first stage. After it drops down, okay, now you have the initial separation. So in this section, as you can see, the liquid separation actually happens between oil and water. So before I go further, this is the water bucket, this is the oil bucket, this is your two-phase oil and water section. But where is the mist extractor?
Right there, that screen.
So do you think the location is right here?
Yeah, otherwise you wouldn't put it there.
So the answer is no. Okay. Why? Because it has to be at the end. So you have to have the gravity settling section. Okay. So all the droplets bigger than 100, okay, have time to actually separate. So the liquid droplets would go on the surface, and the air is free of water in terms of liquid droplets bigger than 100 micron. So at the end, where it is the gas is actually flowing out, we want the mist to be located over here. Okay, so grab the rest of smaller droplets of liquid before leaving and going to the gas compressor. Okay, why don't we want? So again, remember, we don't want any liquid as much as possible going to your gas compressor, and we want actually no gas to go to your pumps or separated either by oil bucket or oil water bucket. Okay. One more question. What is the pressure relief valve? Where is it? Do we have it here? No, we don't have it because we're not going to reach to that pressure problem that they didn't put it here. So, but another question. If we want to put one here, okay, where is the right location?
Where the gas comes out?
Before the emission structure.
So is it here?
No.
Is it here?
Yes.
Yes. Okay. That's where pressure can build up, and you want it over here, so it opens up. Okay. Again. So I know that in the previous session you studied how the separation between water and oil happens. So if someone asks, what is the parameter? What is the different parameter between the two liquids result in the separation? Density. Okay. So again, one more question. So you see we have a liquid column over here, and we have another liquid column over here. I hope that you all can see it. So these two are related through a channel down here. Okay. It means the hydrostatic head that we have over here below this water section should be the same as your hydrostatic head over here. So between oil and water is more dense, okay? Has higher density. And we know it when these two are connected through this channel, okay? The hydrostatic head has to be the same. So rho GH here has to be the same as rho GH over here. However, instead of having the full water, we have a little bit of oil here. Since, as you can see it in your handout, the second page. In the second bit, as you can see, rho H of oil plus rho H of water has to be the same as rho water and H over here. So HO is this. So you all can see it, right? Which one I'm talking about? This one. First one. Okay. So HO is here. HW is here. HW prime is here. Okay. Since density of oil is less, okay, you will have the summation of higher height this side when you compare to this side. You see it? It's visually accessible. See, this one is higher than this. And that's the main function, okay? Now that the system starts working, okay? Oh, sorry. So, oil is supposed to come around this way. So anyway, I hope this goes well. So when the flow rate is too low, what's wrong with the pump? But when the flow rate increases, okay, as you can see, the water column is here, but the oil column is going to be right on the edge. That a little bit more of oil comes in. It's going to drop down to this section, which is called the oil bucket. Okay. So now that it accumulates here, so does the water. Okay. Something should automate, okay, the process of draining water and oil. Okay, so we usually have in the field, we have separator, we have what? Floating valve that regulates whenever it is required, it drains your water and your oil. Okay, here we don't have it, that's why we do the manual drainage. Okay, and that's how it works. Okay. So it is visually you can see it how water, liquid, and gas actually separate. Another question. When you mix two liquids with different densities and viscosities, okay, they form what? Emulsion, right? So when they form emulsion, is it something desirable or not? Absolutely not. Why? Because you cannot separate it, saying that this is water and this is oil because they are well mixed. One of the jobs of this three-phase separator is actually to, so you, for each case, you will have different length and different size of the separator. Okay? This is because of this reason that you need to have enough time for your liquid so the emulsion breaks and separates. So when you drain your water, it's pure water, your oil is pure oil. So again, the length of this liquid section, okay, is for giving it enough time so the emulsion, for example, water droplets in oil or oil droplets in water, okay, can separate. So for that, let's go to the third page, okay, and look at that formula. It's a terminal setting velocity, okay, that is used in emulsion. So let me elaborate again. So when the mixture drops down, okay, let's separate the phases from water to oil. So the droplets of oil, you want it to be in this section. So when it is drained out, okay, it is just oil coming out. But sometimes some of the oil droplets go to this bottom, right? So when you open this up, let me just turn it out again. Okay, oil droplets on the bottom side, okay, as you can see, this time it's working. Okay. And instead of having it flowing out, I have to manually drain it. So when the oil droplets come down over here, okay, by the time it's going to go up, so hopefully it's going to be in the oil side, so it doesn't go to the water bucket, so it does not leave your oil, pure water reserve. So let me explain this way. So when it reaches over here, again, we want to give it enough time so it can reach up over here, so it leaves and drain your oil bucket. And this is where your equation comes into play. Okay, this equation tells, okay, the velocity of your droplet, okay, to move vertically. It gives the speed of those droplets. So let's say you have delta Sg, which is the difference of density of your liquid, which is water and oil. What is dm?
Size of the droplet.
Droplet size. If you have, okay, when you talk about the emulsion, you usually have continuous phase, okay, and you have droplets. This dm is for droplets, okay. What about mu, viscosity? Is it the average viscosity of the fluid, or it is the continuous phase, or it is a droplet phase?
Continuous phase.
Continuous phase, okay. So you have all the information over here, so you know. And one more question: you want this number to be high or low?
Low.
You want it to be high. Terminal velocity. Okay. So it says for let's say, so it means it's going to be, so you have the second on the denominator, okay? When it is high, it means it's going to move up or vertically faster, okay? So that's going to be really high. But we're talking about the vertical, we're talking about the vertical direction, okay? What does it have to do with here? Because we're talking that we want the oil droplet which is where is here, okay, to go up, right? But we just talked about the vertical. So how do we account for the horizontal velocity? So what do you think? Okay, what's your name?
Oh,
What's your name?
Christian.
Christian. So can you just guess how can it be related? Okay. Let me help you. Think of it as in terms of time. In terms of time. Okay.
Talking about viscosity, right?
No, in terms of time, that if we give it enough time, okay, that vertical direction movement, okay, is going to be enough. So let's say this. So let's say oil droplet is going to move this fast up, okay. If the flow is so fast, okay, it will not have the time, okay, to reach to this section, because while the
Just keep
vertical
increasing.
while the vertical velocity is this much, since the flow to the horizontal direction is too fast, it's going to move it to the water bucket. So the velocity or the flow rate of your stream, okay, is very important.
So you want it to be slower.
You want it to be slower, or you want this section to be longer. When it is longer, okay, it's going to have enough time to reach to the surface, so it does not go to your water bucket. Is it clear? So let's do this then. Let's go to the calculation side of it. But can we quantify what we just explained? Yes, we can. We have the mixture flow rate, right? Volumetric flow rate. Also, if we assume that in this half circle surface, okay, everything moves at the same speed, so we treat it as average velocity. It means whatever you see here in this half circle surface, okay, it's going to move with the same speed. Can we get that speed? Yes. Volumetric flow rate divided by cross-section area, okay, it's going to give you the velocity in the horizontal section. Okay. So we have the velocity. What is velocity formula? What is the unit? Feet per second. Let's talk about that second. We already know the time, okay, that we want the emulsion to get out of the bucket, okay, based on this formula. Okay, we have the horizontal velocity now. So V equal, okay, distance or length over time. We know the time that we want to give our motion. We know the horizontal velocity, and the denominator is going to be the length. Is also going to be known, which is the length of this. This is the first design criteria that we want to keep in mind. How long you want the liquid section or liquid collection section to be, right? Is it clear now? Okay, can someone explain what happened? We talked about oil droplets over here, okay? What about water droplets in the oil side?
Hey, can you go back over the time part for a second? You said that, like,
Yeah.
basic calculation you can do how long, like, we did?
Yeah.
Yeah, how was that? How was it, like, time variable or anything?
So go to the velocity over here. Okay. So if you have the velocity, you also assume that you have the length, okay, which you want to calculate. This is an unknown, okay, right?
What are you saying? So you just solve for the time?
Yeah, solve for the time. Yeah.
But I thought the velocity that's in this equation is just the vertical velocity from the water goes down. Which equation is the
Okay, yeah. Okay.
The
Let me explain. That's a good point. So when you have water droplet, when you have oil droplet over here, okay, the distance over here is in the vertical section. So you want it to go at least, okay, this much, not to grab it, not to lead it to this section. So on the bottom to this interface, let's say this 6 centimeter. Okay. You all see what I'm talking about? This formula is for vertical side, vertical direction. Yes. This is for vertical direction. Okay. So you want to know what is the distance that you want the droplets to go. So it's going to be in a safe side that does not go to your water bucket. And it's going to be to this interface. You want it to be as high as possible, but assume that if you are at this interface, okay, it's going to be safe enough. So you measure the length, okay, from this bottom to the top, let's say it is 6 centimeter, okay, and solve this VT for 6 centimeter of length, and it gives you a time, okay. Then you use that time into your horizontal section, with your horizontal velocity. Okay? Is it clear now? If it's not, let's ask this. Let's make it clear. It's not clear?
No.
Okay. VT is what? Is the vertical speed of oil droplets into the water phase. Okay? Let's put it aside. You want to know?
Everyone, this one work right now. Okay? Is this good? Better? Maybe I have to put this on. Can you put that on the floor? Yeah. Don't face it my way, face it that way, okay? Is it better? Okay. Don't face it my way, okay? I'm one way. Right, so right now it's face it that way. Maybe this better. Now, can you try this? Yeah. I just checked the battery. Is it better? Yeah. Okay.
Sorry about that.
We need earbuds also.
Okay, so at this VT formula that you see over here, okay, is okay. So this VT is for the vertical side of water droplets and the oil droplets in the water. Okay. You want to know what is the time required to go to the interface of water and oil, so we know it's not going to go to water bucket.
I don't think it likes you, Dr. Ecker. Be patient with me a little bit, okay?
Okay. So you see? Okay. So this VT is a formula so you can calculate the time required to reach the surface or the interface of water and oil. Okay?
Yeah.
We need the time now. Let's go to the horizontal velocity that I was talking about. Okay?
Is equal to D over T.
Yeah, so you all agree how to calculate the horizontal velocity because you have volumetric flow rate. If you divide it by the cross-section area, which is the half circle if you see it from this way, you get the horizontal velocity in the horizontal direction. Okay? So now you want to make sure, okay, the length that you have is long enough so your retention time from the motion that we discussed, okay, is enough. So you put the equation as V to the velocity equal to delta x, which is here, and the time that we previously calculated from the VT emotion, what is it called? It's called the Stokes law. Okay, so is it clear?
Can you repeat the equation?
Here it's written here. Stokes.
For the horizontal, you said we divide by which area?
Cross-section area, so.
Which cross-section area?
So, let me open this page. Turn this on.
What page is that? I don't think we have that.
The second one.
Yeah.
Oh, third one, yeah. So, if you see, okay, your flow is toward this way, right? So, the direction is this. What is cross-section area? Is the one that is 90 degrees away. Okay? So, it is half circle. Okay? That's
Can we see your paper? I don't think we have it. It's a third page.
third page.
It's this one.
Oh, yeah, the second page.
What is this one? Is that the emotion?
What is it?
Is that the emotion that you're talking about?
What is it? Solid particle.
This is first, second,
Yeah.
and it's third.
Solid particle.
This is different. Maybe someone wants something I don't know either.
So we're supposed to solve the horizontal velocity using Q over A, right?
Yes.
And then you solve the length using your velocity, your horizontal velocity. So when do you use your VT?
You calculate VT.
Okay, that's what we're looking for.
Yeah. And then you have VT, okay? So from this equation, you want to know the time, okay, required for a motion to go up to the surface of gas and oil and water.
Right, but
So basically, you're looking for time. Then you get the VT from this equation. Okay, again, delta x over t is going to be VT, and delta x is the vertical number.
yeah, I guess what I'm asking is what the horizontal velocity and the length have to do with this equation.
So in this equation, you want to know, okay, how much time you need. Okay, so you make sure the droplet over here goes to the surface.
Mr. Shadi, I have a question.
Yes.
So first step, we calculate the velocity Q over V to get the what? Vertical velocity. And then what do we do next?
We get
So-
the horizontal velocity.
We horizontal velocity.
And then we calculate the time. No, we calculate the horizontal velocity using the changing length divided by the time. Right?
No, I thought we already calculated that using Q over A.
So you have the, okay, all we care about is the length of this section, which is liquid and oil, right? You agree?
So it's just
Okay.
the time.
Oh,
So the time also is important so that we make sure complete separation here happens. Complete separation means what? It means the emulsion or the droplets of oil that came down over here have enough time so it can go up while it was moving. So when it is moving, it's going up this way. In that formula, simply it says the vertical movement. But now that we have flow to this direction, it's gonna move up this way. Right? So we know the time, okay, that it is required to give whatever flow direction is, okay, for the droplets to go to the oil side.
Right.
So that's why when we calculate the horizontal velocity, okay, we put that time into the denominator and calculate the delta x to make sure that this length that we have is enough for complete separation.
And to determine that time, it's VT, the velocity it takes for the oil droplet to move up, is equal to the distance, that height, over time, and then we solve for time.
Uh-huh.
And then we use that time
Right.
to solve for the length using the horizontal velocity.
so we use the time from the
Question, more question, more
Yes,
question.
yes.
Yes, there's a question.
But you just said it was the length over time, though. So how are you going to calculate two unknowns with only knowing VT?
You know VH, you're determining length, and you know time.
The horizontal
Where'd you get the time
velocity.
from?
So,
Vertical velocity? So we use the time from the vertical velocity.
so like you have this, so then you do VT is equal to your dy, which is the distance from what it moves, and then you solve for this t. Then using this equation, you have your VH, you're going to determine this length, and this time goes down.
Oh, so you're just finding, okay, so you're finding your VH, and with that you're going to find, you already know your
T,
your
you already
delta
know
X?
No, that's what you're finding, delta x. Delta x.
You got your T from your
Yeah.
vertical.
This one right here, because the velocity is distance over time right here.
But what I'm saying is we have to know dy in order to calculate time.
Yes, and dy is the length from the bottom of the vertical length. So from the bottom of the separator to the top of your emulsion.
Okay, okay. So then you get that time,
Yeah.
put it in here, solve for delta X.
Yeah.
Why aren't those equations?
Drop the diameter to different
So you just use step by step.
viscosity and the viscosity of the continuous phase. So this will be known. Okay. The second thing, everything here is known. Also know the delta x, the vertical direction. What from the bottom of your water section to the interface? You said could be 6 centimeters. Okay?
right? So now we're going to write it this way. Delta x over time, and it's going to be this bt that we have. Let's say, I don't want to give numbers, I don't know. So you have the this, so we have this way. Okay, so now that so delta x vertical multiplied with time, which you don't have it, will be equal to bt that we have. Right? This is calculated by multiplying bt over delta x vertical. Any question now? Okay.
Let me ask them. Do you understand? Yes. You understand?
Yes.
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 Very easy. Clear enough?
Yes.
All right. They have it.
Okay. Then you have this T over here. So we go to the second part. What is B horizontal? It's the Q of mixture over the cross-section area. Okay? So now that we have this one, let's say our horizontal line is known. What is the formula for horizontal line again? Delta x this time is horizontal. Multiplied by time is going to be the same as this one. So the time then has to calculate the edge multiplied by delta x horizontal. This is known.
You solve for VH.
You have to solve it for
So then you solve for
delta x. So your delta x horizontal is going to be VH multiplied by t. That's it.
That's for the horizontal. Here though?
Yeah.
Or is that the whole freaking thing? I would think just that one, because that's the only set. So they're gonna. Where's
I just wrote it like this. Like I just wrote like 4 steps to solve for it.
Yeah.
Okay, I have a question for someone smart. This guy.
Where's the given date? They're asking all these questions.
So this is, but this is for oil droplets in the water slide to go to the bed. How is that? Can you write down the solution? Okay, for water droplets on the oil side, okay, need the very top to go to the bed. So it's not going to go to the oil bucket. So you have a proper separation. What would be the difference here? So the formulas one hand are going to be the same. Okay, but look at the parameters inside the okay, so it's okay. No one this thing here is the same. Okay, this A is the same. So everything here is going to be the same. Right? We want to see how it will be different. If now we want to take care of the water droplets in the oil side on the top to go down. So the only difference we saw, this is going to be the same. The only difference is this formula. Okay, and over here as well. So in this formula, it's EM is for the diameter of what? Water droplets. Because now we talk about water droplets. And what is this delta is vertical? Is the vertical of oil. So now the water droplet wants to come down. So that's why it has to pass. Okay? The whole oil column. That's why your delta is vertical. Is the oil column now. Is it clear now? It's going to be the same. All you have to do is to have to relate time from vertical direction to the horizontal direction. Okay. More questions?
It's from the bottom to the emulsion light before it starts spinning.
So that's gonna stay the same.
No?
It'll stay the same. If we're solving it for the road, I thought he just mentioned it.
Okay, guys, I have something new to show you.
Yeah, let's go.
Okay, do we have good separation or not?
Yeah.
Who say yes?
Good separation.
Good separation. Yes or no?
Yeah.
Yes, wrong. Look at this. We have gas in water line. We don't want gas in water line. We have vortex over here. We have gas going to oil line. We don't want that. So this is bad.
How do you know we have gas?
Look at the vortex. Come closer. Don't kick my camera, but just come closer. Okay? See, when you look from the top, there's a vortex. It's like a tornado.
Well, it's a vortex because you have the valve open, isn't it?
So, and you see this part? So if the dump valve work correctly, be careful with my camera. If the dump valve work correctly, so the dump valve close.
It's because he had the valve open, so there was a vortex, so the gas
So
was.
if I open the valve, you look from the top, it look like a vortex. Like a toilet. Like a toilet, yeah. And this line have gas. So that's not good. This is like malfunction of the dump valve. Bad separation. Okay.
My dick out and show on the camera.
Yes, it should not
gonna
happen.
come out on here.
Bubble inside. It should not be bubble. Look from the side. Look from the side. Come and look at this way. On the side, you see the camera, you see blue droplet in white layer, white droplet in blue layer.
I just want to chill.
You see the droplet on the side, the left side?
Yeah, it's foamy.
From here, from
This is what you
here.
were talking about in class, the foamy.
Oh, that's the foam. That's the foam thing. In the actual case, the foam is a lot worse because it's real oil. This is just water and oil.
Right, that's freaking conventional.
From the side, you see
like a beer, you
the
just
blue
skip it up.
droplet dropping. Maybe you don't see it. Maybe he see it. Yeah, you have to look from this side. Come this side. Take a look at it.
Watch the camera, bro.
Come from that side.
Don't worry, I got your camera. I'm
On the left side, do you see the dropping of the blue droplet? Blue droplet going down the white layer. You see that?
Oh,
You see the blue droplet dropping? And that's based on the terminal velocity equation. Based on the size of droplet.
camera. No way, camera, get the hell out of the way. Just kidding, not that. I don't know about that hard, bro.
Damn, where you're taking pictures, bro. I see what you're doing.
It says blue dots.
You see the blue dot going down and the white thing going up. Alright?
Thing going up.
The oil going up through the.
So that valve is closed.
That's fantastic.
That's crazy. Makes sense.
See that?
That was like the first one I got.
So what your post was like things don't always go as planned. Did you have like besides Houston
You wanted to work for free in the back here, what does that mean?
Okay, one important question. So at the end, which is the size of the drop, okay, over there. We said we already know it. How? Okay, the viscosity we know about the density we know. What about the droplet diameter?
Is there like a standard or something or not?
It is given by this equation.
Okay. So based off the viscosity?
Yeah. Fourth page. Which equation? Fourth page. No, fourth page.
It's on our third page.
It's on the third page first. Yeah, So one question.
Now we good, honey.
We covered it. Question.
Are you done?
We have more time.
Okay, I'm not done yet, but he is done. Okay. I'd like to ask you this.
Do you not like this? Maybe it's too loud. Is it too loud a little bit?
It echoes too much.
We're really
I
close. We can try
would like
it.
to ask you this. How do we know that the separator is big enough? How do you know that?
The line of water needs to be below.
Okay, no water is good separation. What about those velocity that you calculate? Horizontal velocity, vertical velocity? Do we use any of that?
Yeah.
Do they need to be the same? Which one should be more? Horizontal velocity or vertical velocity?
Vertical.
Okay, how do we calculate retention time? What is retention time?
No.
Did you talk about retention time?
Talks about a time.
You said the time was 10.
Retention time is the amount of time that gas molecule or water molecule stay inside the separator. How long does it stay in there? How do you calculate retention time? How much is the retention time in this separator? 10 minutes? 5 minutes? 1 second? Or how do we calculate it?
Do you
Time from
agree?
left to right.
What? It's a little bit tricky,
It's
okay?
dependent.
So what I'm going to do is I assume it's fully mixed in the mixing section. Okay? I calculate those volume, the volume of liquid phase that used for the separation. So when I know the volume of the liquid phase that used for the separation, I know the flow rate of liquid that coming in. Let's say the flow rate that coming in is 10 gallons per day, and the separation volume, this volume is 10 gallons. So the retention time will be 1 day. You agree? Yes. That's how we calculate retention time. That will tell me if the separator is big enough or not. Okay?
Okay.
What about, sorry. Okay, what about malfunction? What about the wear height? The wear height over here, is it good or is too low?
Weird
Do
height.
you know if you raise the wear height, how much happens?
What are you considering the weird? Just that little section or
Far right.
far right?
This one is low. Change it, the height
yeah.
of,
You can lift it up, down.
yeah,
You can go up,
the
down.
height of this wear is going to change it. Okay?
Looked fun to me.
Yeah. So what happens if it's too low? Tell me something.
The mixing section, but I don't know.
It's probably not.
So if it is too low, okay, actually,
Should this height be the same as that height? Should
No.
this wear height be the same as that wear height?
not necessarily.
Not necessarily. How much should be the height?
So if you adjust this over here, okay, the water comes on the top, okay. If you get it higher, okay, you'll have more oil coming out because the hydrostatic head here is going to be higher. So the length over here, the height over here is going to be higher as well. So you see.
Just keep overfilling.
So this height control the oil film thickness. If you want oil film thickness to be more, you do what?
Increase the
Lowering it down.
No.
Okay. If you want this to be thinner, you make it go up. So in the actual case, we cannot move it up or down. We just lie it.
Let me tell you what, because the
Yeah, making a sense,
hydrostatic is
didn't
going to
it?
be high.
No, prove it. Can you prove that? Can you prove it?
Yeah.
Could have sworn it was the other way.
I know. You want it thicker, you raise it
It
up.
takes a while to reach equilibrium. Okay. When he adjusts it, they may not do anything yet.
We'll catch it tomorrow.
It's not a burger.
So if this height is high,
Right.
so this means the right hand side needs a lot of hydrostatic head. The only way it can have a lot of
So wouldn't it be
hydrostatic
thicker?
head is
That's what I said. That's what
the height of water has to go more. See what I'm saying? So the oil gets thinner.
Where's the water spill?
So the oil gets thinner when you raise or lower it?
Raise.
Okay, so you stay over here.
Yeah.
under the weir.
Okay.
No,
Like an okay. All right.
there's an opening under the weir.
Gotcha. Yeah. What? Oh, that leak is defective over here.
Oh no, it's because of the
Okay,
raising.
now here's the weir.
Because if you raise the
Now
rear
it's
height,
rising.
you can allow more water to
It's
come this
thicker.
way. That's not very intuitive.
It does not make sense.
Why?
Do you see it?
What the hell are you talking about?
Pressure. So you're saying if we raise this, it'll allow more water to come over here?
Water is not
Yeah, that's what I'm saying. It comes over.
So raising
Any
it.
pressure you still turn it on? Like all the
It's all about
Yeah, no, cause it's because the
When we raise this up,
You know the
it
road
means higher water height over here.
Right.
Okay?
Right.
Yeah.
On the other side, and the other side, okay, you cannot have higher height because it's gonna pour down.
Right.
Instead,
Oh, it gets
okay,
heavier fluid.
Instead, water column is gonna get bigger,
So it can account
okay?
for the.
So the hydrostatic change.
Right.
Now
Okay,
the
so it's.
water's getting pushed this way.
Do you understand it now?
Oh, I'm not side, the side has shade.
What did he say, Chris?
So since you're increasing this, your water height's going to get here, so your hydrostatic's going to increase.
Yeah.
But since you can't raise this high, you have to offset it by getting a heavier fluid. So you displace more oil and get a thinner oil column and have a higher water column in order to try
Whenever,
to equate.
whenever the weir plate is higher,
Yes.
right? You have
get
a thinner oil.
to get more water because of heavier fluid
Heavier fluid.
to try to.
So they're kind of trying to balance each other
Right,
out. Okay,
right.
that makes sense.
That makes sense.
That does make sense.
You do a great job, right?
Is that it?
Next session, I will be here, okay?
What is this for? We have to turn this up.
You keep it. And the solution will be processed. You don't need to submit anything. When this go up, we need denser, thicker level of dense liquid, which is the water. So water level has to go up.